Hello, how are you? My name is Fávero and I'll present the paper titled A Novel Single Propagation Path Multimode Power Amplifier, authored by Fávero Santos, Professor Bernardo Leite, and Professor André Mariano. We are all members of the Group of Integrated Circuits and Systems at UFPR in Curitiba, Paraná, Brazil. I hope you all have a wonderful time while accompanying this presentation. In this presentation, we're going to talk about a circuit that allows a single propagation path single-mode power amplifier to behave as a multimode power amplifier. To explain that idea, basic concepts will be discussed and gradually expanded. A proof of concept will be presented, and a comparison to the state-of-the-art will be shown. For your later reference, I added this slide with the structure of topics. Feel free to use it while reviewing this presentation. A technical trend in mobile wireless communication systems is the smart use of energy. Smart use of energy roughly means that available energy usage is modulated based on power consumption profiles. The smart use of energy allows a higher overall efficiency of the system, as those power consumption profiles tend to be optimized for the different scenarios of the application. Modern examples of such trend are the transmit power control and the time to wake up mechanisms available in the IEEE 11AX wireless standard. The TPC allows the dynamic adjustment of the DC power consumption based on the magnitude of the output power needed. This means that for lower output powers, lower DC power consumption is employed, and for higher output powers, higher DC power consumption is employed. This mechanism allows an overall optimization of the system efficiency, an important characteristic for mobile wireless systems. The TPC mechanism, in specific, presents itself as a design opportunity at the phi level of the transmitter system. It matches well with the multimode power amplifier architecture. Multimode power amplifiers are power amplifiers capable of operating with different and selectable efficiency profiles. In this context, efficiency profiles are related to the capacity of achieving peak efficiency levels for different output powers. To better clarify this concept, let us compare a single-mode power amplifier to a multimode power amplifier. The efficiency performance as a function of the output power for a typical single-mode power amplifier is presented in this slide. As shown, there is only one curve with a global peak efficiency. It is said in this configuration that the amplifier has only one unique overall efficiency profile. Let us look at the multimode power amplifier. The most protruding characteristic of this type of system is that now there are several efficiency curves that describe the power amplifier's efficiency. Each one of those curves is a different efficiency profile with its own maximum efficiency and output power range. Apart from that, another central concept is that operation over any curve can be selected to match the needed output power. Now, allow me to explain what the advantage is of using multimode power amplifiers over single-mode power amplifiers. Let us consider two hypothetical power amplifiers that are the same, except by the fact that one can behave as a multimode power amplifier, while the other one just as a typical single-mode power amplifier. If an output power is selected in each system and are made equal, the resulting efficiencies will be different. It so happens because the multimode power amplifier can change its efficiency profile to the one that allows a higher efficiency for the intended output power, while the single-mode power amplifier must maintain itself in a single fixed efficiency profile. That being said, one can separate multimode power amplifiers into two different classes: the single-path multimode power amplifier and the multi-path multimode power amplifier. The single-path multimode power amplifier is a power amplifier configuration where the RF signal is not relayed or divided to parallel power structures and yet can provide multiple efficiency profiles. A multipath multimode power amplifier, in its turn, is a power amplifier configuration in which the RF signal can be relayed to several parallel power structures to provide multiple efficiency profiles. Several examples of multimode power amplifiers can be found in the literature. For example, in Modesto et al., a 12-mode power amplifier is proposed by enabling or disabling different aspect ratio parallel cascade power cells. Another example is the one presented in Luong et al., where a 4-mode power amplifier is achieved by enabling or disabling a double cascade power structure. In O et al., yet another type of multimode architecture is presented. In specific, it uses equal aspect ratio parallel cascade power cells to obtain a dual-mode power amplifier. Finally, in Kwong et al., a technique to alter the architecture of the circuit is employed. In this circuit, two power modes are obtained by changing the architecture from cascade to stacked and vice versa. As we briefly observed, there are several methods to obtain multimode operation if the activation or deactivation of parallel power structures is employed. In this sense, if compared to the single propagation path, the multi-propagation path is the most common type of multimode architecture found in the literature. Well, because achieving multimode operation via parallel power structures is a natural idea. Multimode operation in a single propagation path power amplifier, however, is not as common to be found as a multipath multimode power amplifier, and sometimes may even seem counterintuitive. In a general overview, if we compare multipath multimode power amplifiers with single-path multimode power amplifiers, the latter has the advantage of using less circuit elements, as there is no need for parallelization of power cells, nor need for switches to relay the RF signal to those parallel power cores. In this sense, this work contributes by proposing a novel single propagation path multimode power amplifier named hybrid. The name hybrid stems from the fact that a transistor can behave as a switch or as an amplifier in this single propagation path architecture. Let us take a deeper look into that idea. The central idea behind the hybrid is that for a stack size of n transistors, some of them can behave as amplifiers A and some of them can behave as switches S. Let us look at a common stacked power amplifier architecture with a stack size equal to 3. In the stacked architecture, all transistors behave as amplifiers. In this type of configuration, all transistors cooperate amplifying the voltage, and thus the output power at the drain of T3 is at its highest. When T3 operates as a switch and not as an amplifier, the output power delivered to the load via T3's drain is lower than the previous case. If the process is continued and now T3 and T2 they both operate as switches, even lower output power is delivered to the load. Observe that three distinct efficiency profiles are available for usage. In general, as we move from scenario A to scenario C, transistors in the stack change its operation from amplifier to switches, and thus output powers differ from each power mode. As the peak output power now is different for each case, so it is the efficiency profile at each case. Regarding the general rules of design, any transistor above T1 may behave as a switch or as an amplifier. The transistor behavior from saturation to triode and vice versa is changed by selecting the appropriate bias. The gate capacitance and supply voltages must be set accordingly to avoid breakdown and to reduce power consumption. The biasing rules for the hybrid configuration can follow the same biasing rules used for the stacked architecture, except when transistors behave as switches. Let us look at the AC voltage swings in a hybrid under the condition of three transistors behaving as amplifiers, T1, T2, and T3, and one as a switch, T4. As presented in this figure, V sub dt3 and V sub dt4 voltages are almost the same, indicating T4's switch behavior. Observe now that V sub GT4 is equal to the sum of V sub DT3 and the DC biasing at the gate of T4. This happens because V sub DT3 is copied to the gate of T4 via the parasitic capacitance C sub GS. This copy mechanism is beneficial to the structure because the transistor operates as an AC modulated switch. Considering the previous concepts discussed, I would like now to present a proof of concept power amplifier. This power amplifier is composed by an input impedance matching network, by an output impedance matching network, by a biasing tree and supply voltage pins, by a hybrid power core of size 4, by a capacitor bank, and its enable pins. At high power mode, the supply voltage is set to 3.8 volts, and all transistors operate as amplifiers. The biasing is properly selected. The capacitor bank is set accordingly. At medium power mode, the supply voltage is set to 3.2 volts and T4 now operates as a switch due to VB4 being equal to 4.8 volts. The proper capacitor bank is also set. Finally, at low power mode, supply voltage is set to 2.6 volts and T4 and T3 now both operate as switches due to VB4 and VB3 being both equal to 4.8 volts. The selection of the proper capacitor bank is also made. The circuit's layout was prepared, RC parasitics were extracted, and post-layout simulations were run. At 2.4 GHz, the three modes of the power amplifier perform as presented in the table. The curves that are presented in Figure 9 are the three different efficiency profiles of the designed proof of concept. Depending on the needed output power, each mode has a range of improved efficiency. For example, from output powers of 17.5 dBm to 20 dBm approximately, the medium power mode should be selected because of its higher efficiency. For an output power higher than 20 dBm, high power mode should be selected because it is the only mode that can operate efficiently above those power levels. For output powers lower than 17.5 dBm, low power mode should be selected because it has the highest efficiency on that range. Please refer to the paper for additional results considering efficiency and output power as functions of frequency and as parameters. Regarding a comparison with other works available in the literature, the presented work stands out for its high efficiencies. Additionally, obtained output powers are in accordance to those presented in the literature, especially if we consider that the presented work is not a differential circuit. Our remark on this slide is that the results of this work and from Modesto et al. Were obtained from post-layout simulation, while works from Wang et al. And O et al. Presented measurement results. One should have in mind that the performances of fabricated and simulated circuits may differ significantly. In conclusion, it was discussed in this presentation a novel single propagation path multimode power amplifier, which uses as its main concept of design the selection of the operation region of transistors in a single propagation structure. Due to this characteristic, the architecture was called hybrid. To validate this idea, a proof of concept power amplifier operating at 2.4 GHz and employing 130 nanometers RF CMOS process was designed. In overall, the proof of concept presented similar continuous wave power performance to those found in the literature, while standing out due to its high efficiency. With those final remarks, I would like to thank you for the time and patience while accompanying this presentation. I hope you all had a wonderful time and that this idea may somehow affect positively on your work. Thank you.